So the last couple of lectures, we developed these formulas here for determining the probability that one event happens given that we already know a second event has happened, a so-called conditional probability. So what we want to do in this lecture is we're going to see if we can generalize this to a situation where we have a sample space that's divided into k disjoint subevents. What we want to be able to do is look at another event, call it A, and calculate the probability of one of the B's given A, assuming that we know the probability of A given each of the B's. All right, now I know that's a little much to take in, right? So let's jump in and look at our example here. Suppose we have two jars. One has 2 green balls and 3 red balls, and the other has 4 green and 5 red. We're going to assume that someone does two things. First, they pick a jar at random, and then they pick a ball at random from that jar. So what I want to know is, what's the probability that the ball came from the first jar if we know that it's green? Okay, so first let's define our events. The event G is going to be a green ball was chosen. Event J sub 1 is going to be the ball came from the first jar, and J sub 2 will be the ball came from the second jar. Okay, so there's a couple of probabilities that we just get for free. The probability of selecting from the first jar is the same as the probability of selecting from the second jar. They're both 1/2, right? Equal chance of picking either jar. Okay, the probability of selecting a green marble, given that we're looking at the first jar, is 2 out of 5. 2 green balls out of 5 altogether. Similarly, the probability of drawing a green ball from the second jar is 4 out of 9. Now, the probability of selecting the green marble and the first jar is, using our conditional probability formula, the probability of selecting the first jar times the probability of selecting a green marble given that we selected the first jar. All right, so we're just going to multiply those two probabilities together. 1/2 times 2/5, that's 1/5. Okay, now look at the other side. What's the probability of selecting a green marble given that, what's the probability of selecting a green marble and the second jar? Same formula, right? Conditional probability formula again. The probability of selecting the second jar is 1/2. The probability of selecting a green marble from that jar is 4/9. Okay, so the total probability here is just 2/9. All right, now I want you to think about the probability of selecting a green marble. There's only two ways that can happen. Either we select it from the first jar, or we select it from the second jar. Because those probabilities are disjoint, this is just the sum of the individual probabilities which we just calculated. So this comes out to 1/5 plus 2/9, or 19/45. Okay, I'm out of space. All right, hold on to those numbers. There they are again. Those are the three things that we just calculated. All right, now, what I want to do is I want to calculate the probability of selecting the first jar given that the ball is green. This is what we were actually asked to find. Right? If you look closely at the end of the last sentence, what's the probability that the ball came from the first jar given that it's green? Right? This is what we're looking for. And again, I've just got our conditional probability formula here, right? And now we know what these things are. This is why I invested so much energy calculating P of G, right? If I put 1/5 and 19/45 into the formula, we get the answer to our question. It's 9/19. Okay, great. We've answered the question. Okay, but I want to see if we can really make this into a little more of a formula based on our calculations. All right, so jump back up to the first line there. P of J1 and G, that was P of J1 times P of G given J1. That was the conditional probability formula that we used to calculate that numerator part. Now remember how we got P of G? That was the sum of the two and probabilities that I've got over here on the left-hand side. So if I make that substitution, the formula looks like this. Okay, what I have here is the formula for Bayes' theorem in the special case that the sample space is divided into two groups. If you think back to the diagram I had on the original page, right? I don't know, 7 or 8 slices, right? If we just had 2, this is what the formula would look like. Okay, so how does this generalize to the case where we have k divisions? Well, it looks like this, right? The probability of b sub k given a is equal to, we've got the probability of a given b sub k times the probability of b sub k in the numerator, and the bottom is just the sum of all of those conditional probabilities over all of the values of I, right, over all of the subpartitions. Now, what I want you to notice here, that's a practical matter. Think, okay, when am I going to use this formula? Okay, the right-hand side, I want you to notice all of the probabilities over there, all the conditional probabilities, are the probability of A given one of the B's. Now look at the formula on the left-hand side. That's the probability of one of the B's given A. So it's just kind of a practical sense. What this formula is doing is it's giving us a way to switch a conditional probability, right? If we have A in terms of the B's, then we can switch it around and get one of the B's in terms of the A. So that's what we're getting from this Bayes theorem formula. Okay, so in the next lecture, we're going to look at an example of this. We're going to talk about a situation that comes up a lot in medical research. We're going to talk about how we can use Bayes' theorem here to make calculations about what are called false positives and false negatives in medical testing.